Imagine that inside the Earth there are two structures you have never heard of, heavier and hotter than everything surrounding them, existing perhaps since the very birth of the planet, and that right now, at this moment, they are determining where the next major eruptions on the surface will occur. Imagine that every major mass extinction over the past 300 million years was connected to them, and that we discovered their existence less than 30 years ago. Geology is the science of what happens beneath our feet. Sometimes what lies beneath our feet turns out to be something so vast that it does not fit into any familiar category. Before we go further, please subscribe to this channel. Your support makes this work possible, and it genuinely matters. Thank you. Now, 2,900 kilometers beneath the surface of the Earth. That number deserves a moment. 2,900 kilometers is not a depth that human intuition handles well. The deepest mine ever drilled, the Tautona gold mine in South Africa, reaches approximately 3.9 kilometers below the surface. 2,900 kilometers is 740 times deeper than that. The deepest scientific borehole ever drilled, the Kola Super Deep borehole in Russia, which took nearly 20 years to complete and reached temperatures above 180 degrees Celsius, penetrated approximately 12 kilometers into the Earth before the project was abandoned because the rock at that depth was behaving in ways the engineers had not predicted. 2,900 kilometers is 242 times deeper than the Kola borehole. At 2,900 kilometers, you are at the core mantle boundary, the most dramatic internal boundary on Earth. Above it, the mantle, a layer of rock approximately 2,890 kilometers thick, comprising roughly 84% of the Earth's total volume. Below it, the outer core, liquid iron and nickel, generating the magnetic field that protects this planet's surface from the solar wind. The boundary between these two materials, between the silicate rock of the mantle and the liquid metal of the outer core, is one of the sharpest compositional boundaries in the interior of any rocky planet in the solar system. The temperature difference across it is estimated at approximately 1,000 degrees Celsius over a distance of a few kilometers. In terms of thermal gradient, it rivals the surface of the Sun. And it is at this boundary, sitting directly on top of the liquid iron core, pressing down from above and heated from below, that Tuzo and Jason live. These are not their official scientific names. Officially, they are the African Large Low Shear Velocity Province and the Pacific Large Low Shear Velocity Province. In the technical literature, they are abbreviated as LLSVPs, pronounced as individual letters. But the geologist Kevin Burke, who proposed their informal names in 2011, chose something more memorable. He named them after two of the most important figures in the history of plate tectonics. The Canadian geologist John Tuzo Wilson, who first proposed the concept of mantle hotspots and tectonic plates in the 1960s, and the American geophysicist W. Jason Morgan, who developed the modern mathematical theory of plate tectonics and mantle plumes in 1971. The names Tuzo and Jason are increasingly used in the scientific literature, and they will be used throughout this film. Tuzo sits beneath Africa and the eastern Atlantic Ocean. Jason sits beneath the central and western Pacific Ocean. Together, they occupy approximately 8% of the total volume of the Earth's mantle, or roughly 6% of the entire volume of the planet. To put that in perspective, each of these structures is larger than the Moon. Each one is several thousand kilometers wide and up to 1,000 kilometers tall, rising from the core mantle boundary to roughly 1/3 of the way up through the mantle. The African structure, Tuzo, is approximately 1,000 kilometers taller than Jason, a difference that, as we will see, has significant consequences for the stability and behavior of both structures. They are hotter than the surrounding mantle by somewhere between 100 and 500 degrees Celsius, depending on which part of the structure you are measuring and which research team's model you trust. They appear to be chemically distinct from the surrounding mantle, denser, with a different composition, possibly incorporating material that has not been mixed into the general mantle convection system for hundreds of millions or even billions of years. And they have sharp, well-defined edges, not gradual transitions into the surrounding rock, but distinct boundaries, like walls, that seismic imaging can resolve with increasing precision. Before we go further into what Tuzo and Jason are and what they do, we need to understand how we know they exist at all. Because the answer to that question is one of the most elegant stories in modern geophysics. No one has ever seen the inside of the Earth below approximately 12 kilometers. No drill, no probe, no instrument of any kind has physically reached the mantle, let alone the core mantle boundary. Everything we know about the Earth's interior, the existence of the mantle, the core, the boundary between them, and the structures that sit on that boundary, comes from seismology, from earthquakes. When an earthquake occurs anywhere on Earth, it releases energy in the form of seismic waves, vibrations that propagate through the Earth in all directions simultaneously. Some of these waves travel along the surface, but others travel into the interior, through the mantle, through the outer core, through the inner core, reflecting and refracting at every boundary between materials of different density and composition. These waves eventually reach the surface at seismometer stations distributed around the globe, where their arrival times, amplitudes, and waveforms are recorded with extraordinary precision. The fundamental principle of seismic tomography, the technique that revealed Tuzo and Jason, is identical to the principle of medical CT scanning. In a CT scan, X-rays are passed through the body from multiple angles, and the differences in how they are absorbed by different tissues are used to construct a three-dimensional image. In seismic tomography, seismic waves from earthquakes around the world pass through the Earth from every possible angle, and the differences in their travel times, wave arriving early indicates faster than expected rock. Wave arriving late indicates slower than expected rock, are used to construct a three-dimensional image of the Earth's interior. The critical insight is that seismic wave velocities depend on the properties of the material they travel through. Hotter rock transmits seismic waves more slowly. Heat reduces the rigidity of the rock and lowers the velocity of shear waves in particular. Denser rock transmits certain waves differently than less dense rock. Chemically distinct rock has different elastic properties than compositionally average mantle. All of these variations leave signatures in the seismic wave record that a sufficiently sophisticated mathematical inversion can extract and map. Seismic tomography as a technique emerged in the 1980s and 90s. As global networks of seismometers expanded and computational power reached the level required to invert the enormous datasets involved. The first clear images of the large anomalous structures at the base of the mantle appeared in the mid-1990s. At first, the images were blurry. Global seismic tomography at that resolution could detect the gross features of the structures, but could not resolve their boundaries or internal details clearly. As the technique improved, the picture sharpened. By the early 2000s, it was clear that these structures were not diffuse anomalies, but distinct, bounded bodies with sharp edges and significant internal complexity. The sharpness of the edges was itself a discovery. Early models had assumed that the thermal anomaly at the base of the mantle would be gradational, hotter material transitioning smoothly into cooler material over hundreds of kilometers. What the improving tomographic images showed instead was that Tuzo and Jason have boundaries that in some places are nearly as sharp as physical walls. The shear wave velocity drops by 1 to 3% across a boundary that may be only a few tens of kilometers thick. For a structure that is thousands of kilometers wide, this is remarkable. It implies that whatever material constitutes these structures, whatever makes them distinct from the surrounding mantle, has not been significantly mixed into the surrounding rock over the timescales involved. Something is maintaining the integrity of these boundaries against the relentless convective mixing that characterizes the mantle as a whole. The story of how we know Tuzo and Jason exist deserves more than a passing mention. It is, in itself, one of the most remarkable detective stories in the history of science. A story about reading the interior of a planet from its surface, using nothing but vibrations in rock. Every year, the Earth experiences approximately 500,000 detectable earthquakes. Most are but too small to be felt by humans. Micro tremors, the constant low-level seismic noise of a tectonically active planet settling and shifting under its own weight. But several thousand per year are large enough to send seismic waves propagating through the entire planet. Waves that travel from the earthquake source, through the mantle, through the outer core, through the inner core, and back to the surface on the other side of the Earth, where sensitive instruments record their arrival. A magnitude 8 earthquake releases enough energy to send detectable seismic signals completely through the Earth and be recorded at every seismometer station on the planet simultaneously. The two primary types of seismic waves that travel through the Earth's interior are called P waves and S waves, or compressional waves and shear waves. P waves compress and expand the rock in the direction of their travel, like sound waves through air. They can travel through any material, solid rock, liquid metal, or anything in between. S waves, by contrast, move rock perpendicular to their direction of travel, twisting and shearing the material they pass through. And here is the critical difference. S waves cannot travel through liquid. A shear wave requires the material to have rigidity, the ability to resist deformation, and liquids have no rigidity. This is why the outer core, which is liquid iron, does not transmit S waves. It is how we know the outer core is liquid at all. S waves are also exquisitely sensitive to temperature. The hotter a solid material is, the less rigid it becomes. It approaches, though does not reach, its melting point, and the slower S waves travel through it. A region of the mantle that is 100 degrees Celsius hotter than its surroundings will transmit S waves measurably more slowly than the surrounding rock. This sensitivity is the basis of seismic tomography's power. Temperature variations of a few hundred degrees Celsius in rock 2,900 kilometers below the surface leave detectable signatures in the arrival times of S waves at surface seismometer stations. The mathematical problem of seismic tomography is an inverse problem. You have a collection of arrival time measurements, thousands of earthquake events, recorded at hundreds of seismometer stations distributed around the globe, producing tens of millions of individual travel time observations. From these observations, you want to recover the three-dimensional structure of the Earth's interior that would produce exactly those travel times. The problem is similar to trying to reconstruct the shape of an object from its shadow, except that you have shadows from thousands of different light sources simultaneously, and the shadows are not simple outlines, but complex waveforms carrying information about every material the wave passed through on its journey. The mathematical techniques required to solve this problem were developed in the 1970s and 80s, drawing on methods originally created for medical imaging. The computational demands are enormous. Inverting a global seismic dataset requires solving systems of equations with hundreds of thousands of unknowns simultaneously. In the 1980s, even with the most powerful computers available, global seismic tomography could only resolve large-scale features, structures of a few thousand kilometers. The resolution was sufficient to show that the mantle was not homogeneous, that there were large warm regions and large cool regions, but the details were blurry, uncertain, debated. What changed the picture was two things arriving simultaneously: the global expansion of seismometer networks and the exponential growth of computational power. The Global Seismographic Network, a coordinated system of high-sensitivity broadband seismometers distributed around the world, began expanding rapidly in the 1990s, placing instruments in remote locations that had previously been blank spots in the data coverage. Each new station exponentially increased the number of ray paths sampling each part of the Earth's interior, improving resolution in exactly the areas where previous networks had been blind. The first clear images of Tuzo and Jason appeared in the mid-1990s. The initial papers described two large regions of anomalously low shear wave velocity at the base of the mantle, one under Africa, one under the Pacific. The scientific community received these results with the particular combination of excitement and skepticism that greets any claim about the deep Earth, where direct verification is impossible and every conclusion depends on the reliability of the mathematical inversion and the assumptions built into it. For several years, debate focused on whether the structures were real or artifacts of the tomographic method, features produced by the mathematical algorithm rather than by actual physical anomalies in the mantle. The debate was largely settled by a different type of seismic observation: waveform analysis. Rather than looking only at the travel times of seismic waves, researchers began analyzing the detailed shape of the waveforms, the way individual waves were distorted, reflected, and converted as they interacted with structures in the lower mantle. The sharp edges of Tuzo and Jason produce distinctive waveform signatures. Waves that travel through the boundary of the structures are converted from one wave type to another, and waves that reflect off the boundaries arrive at the surface with a timing and amplitude that is inconsistent with a gradual thermal anomaly, but exactly consistent with a sharp chemical boundary. This waveform evidence, accumulating through the late 1990s and 2000s, convinced the geophysical community that the structures were real and that their edges were genuinely sharp, not the gradual temperature transitions that a purely thermal anomaly would produce, but physical walls between chemically distinct materials. By the early 2000s, seismic tomography had reached the resolution to show not just the existence of the structures, but their internal complexity. Tuzo and Jason are not simple homogeneous blobs. They have internal variations in seismic velocity, hotter regions and denser regions within the same structure. They have irregular surfaces. Their upper boundaries are not flat, but topographically complex, with peaks and valleys measured in hundreds of kilometers. They have what appear to be conduit structures, narrow channels where material rises more rapidly than in the surrounding structure, possibly the roots of individual mantle plumes. And they have the ultra-low velocity zones at their base, the most anomalous seismic regions anywhere on Earth, sitting at the contact with the liquid iron core. The current generation of seismic tomography models, products of research groups at Berkeley, Caltech, Utrecht, and a dozen other institutions around the world, can resolve features in the lower mantle at a scale of approximately 200 to 300 kilometers. This is still coarse compared to what we would need to fully characterize the internal structure of Tuzo and Jason, which contain features at scales ranging from tens of kilometers for the ultra-low velocity zones to thousands of kilometers for the overall structure. But the improvement over the first generation of models is dramatic, and the pace of improvement continues. Each new major earthquake provides new data. Each new computational advance allows more sophisticated inversions. The images are getting sharper every year. The seismologists who produce these images sometimes use a phrase that has a particular resonance when applied to the deep earth. They say they are illuminating the interior. It is exactly right. We cannot reach the deep mantle. We cannot drill to it, fly through it, or send a probe to sample it. What we can do is illuminate it, flood it with the seismic energy of the Earth's own earthquakes. Read the shadows those waves cast as they interact with structures 2,900 kilometers below the surface, and from those shadows reconstruct, imperfectly but increasingly accurately, the shapes of the things that live in the dark. What is the mantle, exactly? This question is worth pausing on because the mantle is one of the most misrepresented layers of the Earth in popular understanding. It is not liquid. It is not a sea of molten rock through which the tectonic plates float like rafts. The mantle is solid rock, crystalline silicate minerals, primarily olivine and its high-pressure polymorphs, at temperatures that would vaporize any metal familiar from everyday life, under pressures that are almost incomprehensible in human terms. The pressure at the core mantle boundary is approximately 140 gigapascals, 140 billion pascals, or approximately 1,400,000 times the atmospheric pressure at the Earth's surface. At these temperatures and pressures, solid rock behaves in a way that seems paradoxical. It flows, not quickly, not on any timescale a human observer could perceive. The mantle flows on geological timescales, with characteristic velocities of a few centimeters per year, approximately the speed at which human fingernails grow. This flow is called solid-state creep, and it is driven by the temperature difference between the hot core at the base of the mantle and the relatively cool surface at the top. Heat rises, cool material sinks. The result, over billions of years, is a convective circulation that stirs the entire mantle, carrying heat from the core to the surface, recycling the oceanic crust that subducts at ocean trenches back into the deep mantle and driving the motion of the tectonic plates on the surface. Tuzo and Jason exist within this convective system, but they are not fully participating in it. They sit at the base, where material is hottest and where the convective upwelling that carries heat toward the surface is strongest. And yet, they persist. They have persisted for at least 200 million years by most estimates, and possibly for billions of years by some of the more speculative hypotheses now being actively explored. In a mantle that is perpetually churning, they remain recognizable, bounded, distinct. Why? The answer, if there is a single answer, is density. The material that constitutes Tuzo and Jason appears to be denser than the surrounding mantle. Not by much, perhaps a few percent. But in a convective system driven by density differences, even a small density excess can be decisive. Material that is hotter than its surroundings tends to be less dense and therefore buoyant. It rises. But if the material is simultaneously hotter and chemically denser, the two effects can cancel out, leaving a structure that is thermally buoyant but chemically heavy, sitting at the base of the mantle in a precarious equilibrium between wanting to rise and being unable to, held in place by its own chemistry. This is the leading model for what Tuzo and Jason are: thermochemical piles. Accumulations of chemically distinct, intrinsically dense material that have been swept to the base of the mantle by the convective currents and pushed into two approximately antipodal positions, one under Africa, one under the Pacific, by the global pattern of mantle flow. The antipodal arrangement is not a coincidence. The two structures are positioned on opposite sides of the Earth, approximately equidistant from the equator, in a configuration that computational models of mantle convection consistently reproduce as the stable two-blob arrangement for material accumulating at the core mantle boundary, under the influence of global mantle flow patterns driven by plate tectonics. But what is the chemical material that makes them dense? This is where the story becomes more complex, and where three competing hypotheses are in active contention. The first hypothesis is the most prosaic and, in some respects, the most elegant. It proposes that Tuzo and Jason are made largely of subducted oceanic crust. Old ocean floor that has been dragged into the mantle at subduction zones over hundreds of millions or billions of years, sinking to the core mantle boundary and accumulating there. Because at those depths, the mineral phases that form from subducted basaltic crust are denser than the surrounding mantle peridotite. On this view, the superblobs are the Earth's recycling dump, the graveyards of ancient ocean floors, compressed and metamorphosed and piled up at the base of the mantle by the inexorable machinery of plate tectonics. A 2025 study published in Scientific Reports, using three-dimensional simulations of global mantle circulation over the past 1 billion years, found that two antipodal LLSVPs developed naturally from the subduction of oceanic crust under the configuration of plates that has characterized Earth over that timescale. The study found that the Pacific structure, Jason, stores approximately 53% more subducted oceanic crust than Tuzo, a consequence of the continuous ring of subduction zones encircling the Pacific Basin for the past 300 million years, continuously feeding fresh material into the Pacific structure. The second hypothesis is more ancient and more dramatic. It proposes that Tuzo and Jason are not products of plate tectonics, that they predate plate tectonics, or at least predate the modern configuration of plates. On this view, the superblobs are survivors from the earliest period of Earth's history, relics of the global magma ocean that covered the entire planet for the first 100 million years of its existence. When the young Earth was so hot from accretionary impacts and radioactive decay that its entire surface was molten. As the magma ocean cooled and crystallized, starting from the bottom up, the first solid minerals to form at depth were denser than the liquid above them. And some fraction of this early crystallized material may have been chemically distinct from what eventually became the average mantle. In this model, Tuzo and Jason are 4 billion-year-old structures, as old as the planet itself, sitting undisturbed at the base of the mantle while everything above them has been recycled, remixed, and reshaped multiple times. New simulations published in 2025 and 2026 have explored this hypothesis and found it physically plausible, suggesting that material contaminated by core composition during the magma ocean era could have accumulated in two stable antipodal locations during the cooling process and remained there for the entire subsequent history of the planet. The third hypothesis is the most startling. It invokes the Moon. Approximately 4.5 billion years ago, within the first 100 million years of the solar system, a Mars-sized body, referred to by planetary scientists as Theia, collided with the proto-Earth in an impact of such violence that it melted both bodies, ejected an enormous disk of material into orbit around the Earth, and ultimately coalesced into the Moon we have today. This is the giant impact hypothesis, the currently dominant model for lunar origin. If this impact occurred, and most planetary scientists accept that it did, based on the geochemical similarity between Earth and Moon rocks, then the collision between Theia and the proto-Earth would have thoroughly mixed the two bodies' materials at the deepest levels. Some fraction of Theia's mantle material, chemically distinct from the proto-Earth's mantle in specific ways, would have been incorporated into the Earth's interior. One hypothesis that has gained increasing traction in recent years proposes that some of this Theian material could have survived as distinct reservoirs at the base of the mantle. If Tuzo and Jason contain Theian rock, material from another planet, incorporated into the Earth during the moon-forming impact 4.5 billion years ago, then they are not simply the Earth's recycling dump or the survivors of a magma ocean. They are something more extraordinary, permanent geological monuments to the most violent event in this planet's history. Distinguishing between these three hypotheses is one of the central challenges in deep Earth geophysics. The evidence from seismic tomography alone cannot resolve the question. It can tell us the mechanical properties of the structures, but not their detailed chemical composition. Indirect evidence comes from the geochemistry of ocean island basalts. The volcanic rocks erupted at hotspots like Hawaii, Iceland, and Réunion, which are believed to sample deep mantle material that has been brought to the surface by mantle plumes originating at or near the core mantle boundary. These basalts show anomalous isotopic signatures, particularly elevated helium-3 to helium-4 ratios, that indicate they contain material that has been isolated from the convecting mantle for very long periods, possibly billions of years. The helium-3 isotope is primordial. It cannot be produced by radioactive decay, and it gradually leaks from the mantle over geological time. Rock with high helium-3 ratios is rock that has been sealed from the mantle convection system long enough to retain a primordial chemical signature. This is consistent with the hypothesis that the superblobs preserve ancient, poorly mixed material, whether Theian, magma ocean, or otherwise. But it does not definitively identify which ancient source that material represents. The question of the superblob's age and origin may remain unresolvable with current technology. The structures are real. Their existence is not in doubt. What they are made of and when they formed is still, in 2025, a genuinely open question in Earth science. The question of what Tuzo and Jason are made of and when they formed is not merely an academic exercise in deep Earth geochemistry. It is a question about the deepest history of the planet. And the three competing hypotheses on the table represent three completely different answers to that history. The subducted oceanic crust hypothesis is the most quantitatively developed and the most directly connected to observable plate tectonics. Its logic begins with a simple observation. The oceanic plates that subduct at trenches, the Pacific Plate diving under Japan, the Nazca Plate diving under South America, the oceanic portion of the Indian Plate diving under Eurasia, are made primarily of basalt. When this basalt enters the mantle and descends to depth, the extreme pressure transforms the basaltic minerals into denser high-pressure phases: garnet, perovskite, post-perovskite, that are heavier than the surrounding mantle peridotite. This density excess causes the subducted oceanic crust to sink faster than the surrounding mantle, accumulating at the core mantle boundary over hundreds of millions of years. Imagine a slow-motion snow globe. The snowflakes, subducted oceanic crust, fall through the mantle over tens of millions of years and settle at the bottom. The convective currents in the mantle are like the swirling fluid in the globe, pushing the settled material into piles in the areas that are not being swept by active downwellings. The areas not swept by subduction, the areas under the interior of supercontinents and later under the Pacific Basin, are where the piles grow tallest. This is, in essence, the model. The subducted crust accumulates over billions of years, swept into two approximately antipodal piles by the global circulation pattern, and those piles are Tuzo and Jason. The prediction of this model, that the Pacific structure should contain more subducted material than the African structure, because the Pacific has been surrounded by subduction zones for much longer, was directly tested by the February 2025 study in Scientific Reports. The researchers ran three-dimensional global mantle circulation models for the past 1 billion years and found exactly this pattern. The Pacific structure stores approximately 53% more subducted oceanic crust than the African structure. The Pacific LLSVP has been continuously replenished by the Circum-Pacific subduction system since approximately 300 million years ago, while the African LLSVP comprises older, more thoroughly mixed material accumulated during earlier phases of the supercontinent cycle. The two structures are not simply two copies of the same thing. They have different ages, different compositions, and different evolutionary histories, products of the same process operating in different geographical contexts over different timescales. But the subducted crust model has a difficulty. Subducted oceanic crust is basaltic in composition, depleted in certain elements, enriched in others relative to average mantle. But the geochemistry of ocean island basalts, erupted at hotspots fed by Tuzo and Jason plumes, shows isotopic signatures, indicating extremely ancient source material. Rock isolated from the convecting mantle for periods exceeding 1 billion years, in some estimates reaching 2 billion years or more. Subducted oceanic crust is recycled material. It was at the surface recently, processed through the oceanic crust generation system at mid-ocean ridges before subducting. It does not naturally carry a 2 billion-year-old chemical signature. Something in the superblobs is older than the subducted crust hypothesis would predict. This is where the magma ocean hypothesis enters. The early Earth, during the first 100 million years of its existence, was a world of fire. The energy released by the accretion of the planet from the solar nebula, combined with the heat of radioactive decay from elements that were far more abundant in the early solar system than they are today, and the energy of the giant impacts that characterized the late stages of planetary assembly, kept the entire surface of the planet molten. The first solid crust that formed cooled, was destroyed by subsequent impacts, and was remelted in a cycle that continued for tens of millions of years. During this period, there was no mantle in the modern sense, no structured convective system, no plate tectonics, no stable surface. There was a global magma ocean, from the surface to the core, in which all materials were free to move and differentiate by density. As the magma ocean cooled, starting from the bottom, where pressure raised the solidification temperature, the first solid minerals crystallized at the base. These minerals were denser than the overlying liquid and settled downward, while less dense material floated upward. This process, called fractional crystallization, would have produced a layered structure at the base of the solidifying mantle, with the earliest crystallized, densest material at the very bottom. If this early crystallized material was chemically distinct from the average mantle, enriched in iron, in certain rare earth elements, in primordial noble gases like helium-3, it would carry a primordial chemical signature that would persist for billions of years if it was never remixed into the convecting mantle above it. The magma ocean hypothesis proposes that Tuzo and Jason are survivors of this early crystallization. Dense, primordial material that settled to the base of the solidifying mantle 4 billion years ago and has remained there, largely isolated from the convecting mantle above it, ever since. On this view, they are not products of plate tectonics. They predate plate tectonics. They may have shaped the conditions under which plate tectonics eventually developed. The high helium-3 ratios in hotspot basalts are, on this model, exactly what you would expect. Primordial helium preserved in rock that has been sealed from the convecting mantle since the very beginning of Earth history. And then there is Theia. The giant impact that formed the Moon approximately 4.5 billion years ago was not a glancing blow. Current models suggest that Theia, a body approximately the size of Mars, with its own differentiated core and mantle, struck the proto-Earth at a velocity and angle that caused the two bodies to partially merge, with a large fraction of the combined material being ejected into orbit around the Earth and eventually accreting into the Moon. The remaining material, the blended mantles of Theia and the proto-Earth, formed the bulk of the Earth's mantle as it exists today. But the mixing was not complete. In a collision of this scale, the violence of the impact would have been sufficient to thoroughly mix the outer portions of both bodies, the portions that experienced the highest temperatures and the most turbulent flow during the impact. But the deepest portions, the material that was already at the base of the proto-Earth's solidifying magma ocean, the most viscous, least mobile material, may not have been completely mixed with Thean material. Alternatively, Thean mantle material, being somewhat different in composition from proto-Earth mantle, may have settled to different depths during the post-impact magma ocean crystallization, creating chemically distinct reservoirs at the base of the mantle. The Theia hypothesis is the most difficult to test directly, because the chemical signatures that would distinguish Thean mantle from proto-Earth mantle are subtle and overlapping. Moon rocks, the best sample we have of Thean material, are remarkably similar in isotopic composition to Earth rocks in most respects, which has both supported the giant impact model and made it difficult to identify a clean Thean signature in terrestrial rocks. Some researchers have proposed that slight differences in tungsten isotope ratios between different types of mantle-derived volcanic rocks. Differences that are being measured with increasing precision as analytical techniques improve may reflect the incomplete mixing of Thean and Proto-Earth mantle material. If this interpretation is correct, and if the anomalous tungsten signatures are associated with deep mantle source regions connected to the superblobs, then Tuzo and Jason may contain rock from another planet, a geological monument to the collision that made the Moon and made the Earth the planet it is today. None of these three hypotheses is conclusively proven. None is conclusively disproven. The most likely reality is some combination, that Tuzo and Jason contain material from multiple origins, accumulated at the base of the mantle over billions of years by different processes operating at different times. Ancient magma ocean crystallization products may form a core. Subducted oceanic crust may have been swept against and incorporated into the edges. Thean material may be present as a minor but isotopically distinctive component. The superblobs are not single-origin objects. They are geological archives, stratified accumulations of deep Earth history, each layer representing a different chapter of the planet's 4-billion-year story. What is not in doubt is what they do, and what they do is extraordinary. The edges of Tuzo and Jason are where things happen. Not the interiors. The centers of the structures appear to be relatively quiescent, insulated from the convective activity around them by their own chemistry and by the dynamics of the boundary layer. But the edges, the margins where the hot, dense material of the superblobs meets the cooler convecting mantle, are sites of intense thermal and physical activity. The core below Tuzo and Jason heats the base of the structures. That heat has to go somewhere, and the place it goes is upward, through the mantle, to the surface. At the edges of the superblobs, concentrated thermal anomalies develop, regions where the heat flux from the core is particularly high, where the temperature gradient is particularly steep, and where the mantle material just outside the superblob boundary is being heated most intensely. These concentrations of heat generate mantle plumes, columns of anomalously hot, less dense rock that rise through the mantle from the base toward the surface, driven by their own thermal buoyancy, ascending through the surrounding cooler mantle over millions of years. When a mantle plume reaches the base of the lithosphere, the rigid outer shell of the Earth, it flattens out and partially melts, producing enormous volumes of magma that either erupt through the lithosphere as surface volcanism or intrude into the crust and eventually reach the surface. The regions at the edges of Tuzo and Jason, where mantle plumes preferentially form, are now called plume generation zones, PGZs. And the evidence connecting PGZs to surface volcanism is one of the most striking findings in modern geophysics. When geologists look at the hotspots, the anomalous volcanic centers that occur far from plate boundaries, where long-lived mantle plumes punch through the moving plates and leave trails of extinct volcanoes as evidence of past positions, and project their surface locations downward to the core mantle boundary, the correspondence with the edges of Tuzo and Jason is remarkable. Hawaii, the most productive hotspot in the Pacific, projects to the edge of Jason. Iceland, sitting on the mid-Atlantic ridge and built by an anomalously thick volcanic foundation. that has puzzled geologists for decades projects to the edge of Tuzo, Réunion in the Indian Ocean. The hotspot whose plume produced the Deccan Traps 66 million years ago projects to the edge of Tuzo. The Canary Islands project to the edge of Tuzo. Yellowstone, the continental supervolcano that sits beneath Wyoming and periodically reshapes the American continent, projects to the edge of Jason. A 2008 study by the geologist Kevin Burke and colleagues examined the locations of every large igneous province, every flood basalt eruption event, younger than 300 million years, and found that all of them, without exception, projected to the edges of Tuzo and Jason at the core mantle boundary. All of them, not most. All. The statistical probability of this alignment occurring by chance is vanishingly small. The implication is direct. The edges of the superblobs are the plume generation zones for the planet, and every major episode of flood volcanism in the past 300 million years, including several that triggered mass extinctions, was ultimately driven by the thermal activity at these boundaries. This is the moment where the superblobs stop being merely interesting and become genuinely consequential for the history of life on Earth. Large igneous provinces, the flood basalt events produced when mantle plumes reach the surface and erupt enormous volumes of lava over geologically brief periods, are among the most catastrophic events in the geological record. The Siberian Traps, which erupted approximately 252 million years ago, released between 1 and 4 million cubic kilometers of lava across an area of approximately 2 million square kilometers. The carbon dioxide and sulfur dioxide released by this eruption, augmented by the burning of coal deposits that the volcanic intrusions ignited, drove ocean acidification, global warming, and the collapse of marine food webs in the most devastating biotic crisis in Earth history. The end Permian mass extinction, which eliminated approximately 96% of all marine species. The Siberian Traps were a plume from the edge of Tuzo, or its predecessor structure, which occupied approximately the same position during the Permian. The Deccan Traps, which erupted between approximately 66 and 60 million years ago, were a plume from the edge of Tuzo. The eruption coincided with, and in the opinion of a significant minority of researchers, contributed to, the mass extinction at the end of the Cretaceous that eliminated the non-avian dinosaurs. The Deccan eruptions released enormous quantities of climate-active gases over hundreds of thousands of years before, during, and after the Chicxulub impact. Whether the Deccan volcanism was a primary driver of the extinction or a secondary factor that stressed the biosphere already reeling from the asteroid impact is actively debated. What is not debated is that the Deccan Traps originated at a plume generation zone at the edge of Tuzo, the Central Atlantic Magmatic Province, which erupted approximately 201 million years ago and triggered the end Triassic mass extinction, one of the 5 great extinctions, which eliminated approximately half of all marine genera and opened the ecological space that allowed dinosaurs to dominate the Mesozoic, originated at the edge of Tuzo. The Karoo-Ferrar, large igneous province, erupted approximately 183 million years ago in southern Africa and Antarctica. and connected to the Toarcian oceanic anoxic event that devastated marine life in the early Jurassic, also at the edge of Tuzo. The pattern is consistent and disturbing. The superblobs, sitting silently at the base of the mantle, generate plumes at their edges. Those plumes rise through the mantle over millions of years. When they reach the surface, the resulting flood volcanism can destabilize the climate system sufficiently to drive mass extinctions. The superblobs are not merely geological curiosities. They are, in the most direct sense, the deep Earth infrastructure from which the largest catastrophes in the history of life on this planet have emerged. This connection extends further back in time than the Mesozoic. The November 2025 study in Nature Communications examined the large igneous provinces associated with the breakup of the supercontinent Rodinia, which existed from approximately 1 billion to 700 million years ago, and found a pattern of 7 sequential LIP eruptions, forming a ring comparable in size to Rodinia that resembles the product of an ancient LLSVP, whose edges advected plumes. This implies that the superblob configuration, 2 antipodal thermochemical piles generating plumes at their edges, is not merely a Pangea-era phenomenon, but has been operating throughout the supercontinent cycle, recycled and reformed as successive supercontinents assembled and broke apart. The relationship between the superblobs and the supercontinents is one of the most active areas of research in geodynamics. The question, at its core, is directional. Do the supercontinents control the superblobs, or do the superblobs control the supercontinents? The case that plate tectonics controls the superblobs runs as follows. As plates subduct at ocean trenches, cold oceanic lithosphere descends into the mantle, eventually sinking all the way to the core mantle boundary. This cold subducted material piles up at the base of the mantle and pushes the superblob material into the regions that are not being subducted, which, by the geometry of the supercontinent configuration, tend to be the regions directly beneath the interior of the supercontinent. The supercontinent acts as a thermal insulator, trapping heat beneath it and generating the conditions for plume formation. When the supercontinent eventually breaks apart, driven in part by the heat trapped beneath it, the plumes that have been building under it are released, producing the flood basalt events that accompany continental rifting. On this view, the superblobs are passive recipients of subducted material, shaped and repositioned by the plate tectonic system operating above them. The case that the superblobs influence the supercontinents runs in the opposite direction. If the superblobs are fixed, or at least relatively stable, features of the deep mantle, then the positions of the plume generation zones at their edges are also approximately fixed. These zones continuously generate mantle plumes, which rise to the surface and weaken the lithosphere above them. Over geological time, the areas of weakened lithosphere are preferentially sites of continental rifting, the places where continents split apart and new ocean basins form. On this view, the superblobs are not passive piles shaped by subduction, but active drivers of the plate tectonic system, determining where rifts form, where new oceans open, and therefore influencing the long-term trajectory of supercontinent assembly and dispersal. The current evidence suggests that both directions of influence are real, that the relationship between superblobs and plate tectonics is a genuine feedback loop, operating on timescales of hundreds of millions of years, in which each system influences the other, in ways that are difficult to disentangle with current models. This is not a failure of understanding. It is an accurate reflection of how a complex planetary system actually works, not as a simple hierarchy of causes, but as a network of interacting processes, each of which is simultaneously a cause and an effect of the others. What makes this feedback loop particularly compelling is what it implies about the stability of the superblobs themselves. If the superblobs are ancient, if Tuzo and Jason are genuinely billions of years old, then they have survived multiple supercontinent cycles, multiple episodes of global subduction reorganization, multiple mass extinction events, and the complete restructuring of the surface of the Earth. They have been heated from below by the core for 4 billion years. They have been swept and compressed by the downwelling currents of subducted lithosphere. They have been eroded at their edges by the rising plumes they generate, and they remain. But not all parts of Tuzo and Jason are equally stable. The 2022 study in Nature Geoscience that documented the 1,000-kilometer height difference between Tuzo and Jason noted that the African structure is taller and has a lower intrinsic density, which means it is closer to the threshold of buoyancy that would cause it to rise from the core mantle boundary and ascend into the mantle. The paper proposed that Tuzo may be in a state of dynamic instability, not about to collapse in any human-relevant timeframe, but geologically less stable than Jason, more susceptible to perturbation, more likely to produce large-scale upwelling events. This matters because we are currently living through one of the most dramatic expressions of Tuzo's activity in the geological record. The East African Rift System, the great tectonic fracture running from the Red Sea in the north through Ethiopia, Kenya, Tanzania, Mozambique, and into the southern Indian Ocean, a total length of approximately 6,000 kilometers, is the surface expression of a mantle plume that is currently active beneath the African continent. The plume originates at the edge of Tuzo. It has been active for approximately 30 million years. Under its influence, the African continent is actively splitting apart. The Somali plate is slowly separating from the Nubian plate along the line of the rift, at a rate of approximately 6 to 7 millimeters per year. 6 to 7 millimeters per year is not fast in any human sense. But maintained over geological time, it is enough to eventually open an ocean. In approximately 5 to 10 million years, if the current rifting continues, the southern end of the East African Rift will be flooded by the Indian Ocean. The Rift Valley, the Great Rift Valley that runs through Kenya and Tanzania, flanked by some of Africa's most dramatic escarpments, will become a new sea. The eastern portion of Africa, the Horn of Africa, Somalia, much of Ethiopia and Kenya will become a new island continent, separated from the rest of Africa by an ocean that does not yet exist. The animals and ecosystems currently inhabiting this region will find themselves on a new island, evolving in isolation, as the populations separated by the new ocean follow different evolutionary trajectories. This is Tuzo at work. Not through catastrophic eruption, though the Ethiopian plateau, basalts, and the volcanic fields of Kenya and Tanzania are expressions of the same underlying plume activity, but through the slow, patient, inexorable application of heat from below, weakening the lithosphere, creating the conditions for rifting and eventually splitting a continent. The Canary Islands, the archipelago off the northwest coast of Africa, are another surface expression of Tuzo. The hotspot that produced the Canaries has been active for approximately 60 million years, generating a chain of volcanic islands progressively older toward the east as the African plate moved over the fixed hotspot position. The most recently active volcanism in the Canaries occurred in 2021 on La Palma, an eruption that lasted 85 days, destroyed nearly 3,000 buildings, and reminded a modern civilization that the forces operating at the base of the mantle are not purely historical abstractions. Iceland, the most volcanically productive land area on Earth per unit surface, is the surface expression of the Icelandic plume, one of the most powerful mantle plumes currently active, originating at the edge of Tuzo. Iceland sits precisely over the mid-Atlantic ridge, and the plume is producing so much magma that the island has been building itself against the erosive force of the North Atlantic for approximately 60 million years. The Icelandic plume is also responsible for the vast basaltic plateaus of the North Atlantic igneous province, the submarine and subaerial flood basalts that were erupted when the plume head first reached the surface approximately 60 million years ago, coinciding with a period of rapid global warming at the Paleocene-Eocene boundary and the mass die-off of deep-sea organisms called the Paleocene-Eocene thermal maximum. Hawaii, the most isolated archipelago on Earth, located almost perfectly in the center of the Pacific Ocean, 4,000 kilometers from the nearest continent, is the surface expression of the Hawaiian plume, which originates at the edge of Jason. The Hawaiian Emperor Seamount Chain, the longest volcanic chain on Earth, stretching 6,000 kilometers from the currently active volcanoes on the Big Island to the ancient submerged seamounts approaching the Kamchatka subduction zone, is the track left by the Pacific Plate, moving over the Hawaiian hotspot for the past 80 million years. Every island in that chain, every seamount, every submerged volcanic peak was once directly over the plume that originates at Jason's edge. The island of Hawaii itself, Kilauea, Mauna Loa, Mauna Kea, is the current position, the point where the Pacific Plate is right now passing over the plume that Jason generates. When you stand on the rim of Kilauea and watch lava flowing into the Pacific Ocean, you are witnessing the final stage of a process that began at the core mantle boundary, 2,900 kilometers below you. The heat that is melting the rock beneath Kilauea was transferred from the liquid iron outer core to the base of the mantle, concentrated at the edge of Jason, and carried upward by a column of anomalously hot solid rock ascending through the mantle over a journey that took millions of years. What you see as volcanic eruption is the surface expression of deep earth heat transport, a connection that runs from the edge of a superblob to the ocean surface in a single, continuous, ancient process. Yellowstone is another edge of Jason expression. The Yellowstone hotspot has been active for approximately 17 million years, and the track of the Snake River Plain, the long, curving volcanic feature running across southern Idaho, is the surface record of the North American plate moving over the Yellowstone plume. The hotspot currently sits beneath the Yellowstone caldera in Wyoming, where a large magma chamber sits approximately 8 kilometers below the surface, generating the geothermal features that make Yellowstone one of the most extraordinary landscapes on Earth. The magma feeding that chamber ultimately derives from the edge of Jason, the Pacific superblob, rising as a plume through the mantle and interacting with the thick continental lithosphere of North America. Réunion, the small island in the Indian Ocean, is the current position of the plume that, approximately 66 million years ago, sat beneath what is now northwestern India and erupted as the Deccan Traps. The plate moved. The plume stayed approximately fixed. The island of Réunion is what that plume looks like today, reduced from the world historical catastrophe of the Deccan eruptions to a single tropical island with one of the most active volcanoes on Earth, Piton de la Fournaise, which erupts on average once a year. The same heat source, the same edge of Tuzo, a different surface expression. The question of whether the superblobs are truly fixed, whether Tuzo and Jason have remained approximately in the same position relative to the Earth's rotation axis for hundreds of millions of years, is one of the most contentious in deep Earth science. The fixed hotspot assumption underlies much of the reconstruction of past plate motions. If hotspots are fixed, then the trails of extinct volcanoes they leave behind are reliable records of how the plates have moved over time. But research published in recent years has found evidence that at least some hotspots, and therefore at least some plumes, and potentially the superblob edges they originate from, have moved significantly over geological time. A study examining the Hawaiian Emperor chain found evidence for approximately 13 millimeters per year of motion of the African LLSVPs since the Oligocene, suggesting that Tuzo itself has moved during the past 30 million years. If this is correct, then the superblobs are not fixed anchors of the plate tectonic system, but are themselves slowly drifting, carried by the same deep mantle flow that carries everything else, just more slowly and over longer timescales. This uncertainty, the question of whether Tuzo and Jason are fixed or slowly mobile features of the deep Earth, has profound consequences for the reconstructions of past plate motions that underlie much of what we think we know about ancient paleogeography. If the superblobs have moved significantly over the past billion years, then every reconstruction of ancient continent positions that relied on the fixed hotspot assumption needs to be revisited. The maps of where the continents were during the Cambrian, the Permian, the Cretaceous, maps that form the foundation of our understanding of ancient biogeography, ancient climate, and ancient ocean circulation, would need to be revised to account for a reference frame that was itself in motion. The ultra-low velocity zones deserve their own sustained attention because they represent the most extreme natural environment inside the solid Earth, and because They sit at the precise location where the story of Tuzo and Jason connects to the story of the liquid iron core below. Imagine standing at the core mantle boundary. You cannot, of course. The pressure alone would compress any material of human scale into a volume smaller than a grain of sand, and the temperature would vaporize any element on the periodic table. But the physics of the place can be described, and the description is worth making carefully. The pressure at the core mantle boundary is approximately 140 gigapascals. To put this number in terms of something mechanical, if you were to take the entire weight of the Earth's atmosphere above a single square centimeter of ground, approximately 1 kilogram, and multiply it by 1,400,000, you would have the pressure at the core mantle boundary acting on that same square centimeter. The rocks at this depth are compressed into mineral phases that do not exist anywhere on Earth's surface. The most abundant mineral in the lower mantle, bridgmanite, a high-pressure form of magnesium silicate, was not confirmed to exist in nature until a meteorite impact in Australia preserved it as a shock mineral in 2014. It is the most common mineral in the Earth by volume, constituting approximately 38% of the planet, and we only confirmed its natural existence 11 years ago. The temperature at the core mantle boundary is estimated at approximately 3,800 to 4,000 degrees Celsius in the mantle just above the boundary, and approximately 4,000 to 4,300 degrees Celsius in the outer core just below it. The temperature difference across the boundary, several hundred degrees Celsius over a few kilometers, drives a heat flux from the core into the base of the mantle that is the ultimate energy source for mantle convection, and through it, for plate tectonics and surface volcanism. In most places along the core mantle boundary, the transition from solid mantle to liquid core is abrupt but relatively smooth, a boundary between two materials with very different properties, but without extreme local anomalies. In the ultra-low velocity zones, something different is happening. The first ultra-low velocity zones were identified in the mid-1990s, almost simultaneously with the first clear images of Tuzo and Jason. The signature is unmistakable in seismic waveforms. Certain S-wave arrivals are dramatically delayed compared to expectations, indicating that in these localized regions, the seismic wave has passed through material that transmits waves at 40 to 50% of the normal lower mantle velocity. To be clear about what this means, the most anomalous ULVZs have shear wave velocities reduced by up to 50%. The interior of Tuzo or Jason shows velocity reductions of 1 to 3%. A 50% reduction is not a subtle anomaly. It is an indication that the material in these zones is fundamentally different, in physical state, in composition, or in both, from anything in the surrounding mantle. 3 explanations have been seriously proposed, and all 3 may be simultaneously correct in different ULVZs. The first is partial melting. At the very base of the mantle, directly above the hot liquid core, temperatures are sufficiently high that some fraction of the mantle rock may be approaching or exceeding its melting point. Not fully molten, the seismic data still detects shear wave transmission, which requires some solid fraction, but partially molten, with melt fractions of a few percent distributed through the crystal structure. Partially molten rock transmits shear waves dramatically more slowly than solid rock, and even a small melt fraction can produce a large velocity reduction. If ULVZs are partially molten mantle, they represent the deepest magma in the Earth. Pockets of melt existing at the base of the mantle at pressures 2.5 times higher than any magma that erupts at the surface. The second explanation is ion enrichment. At the core mantle boundary, chemical reactions between the liquid iron outer core and the silicate mantle are possible. The two materials are in direct contact, and at these temperatures and pressures, iron can diffuse across the boundary, enriching the base of the mantle in iron oxide and iron silicate compounds. Iron-enriched mantle minerals are denser and have lower seismic velocities than iron-poor minerals, and the enrichment could be sufficient to produce the extreme velocity anomalies observed in ULVZs. The iron enrichment model has been supported by laboratory experiments at high pressure, in which samples of lower mantle composition enriched in iron show velocity reductions consistent with ULVZ observations. The third explanation is the most exotic. It proposes that ULVZs contain subducted banded iron formation, ancient iron-rich sedimentary rock deposited in the Precambrian oceans between approximately 3 and 2 billion years ago, when photosynthetic organisms were beginning to oxygenate the Earth's atmosphere. Banded iron formations are some of the most iron-rich rocks on Earth, and the iron-rich layers within them, if subducted into the mantle and carried to the core mantle boundary, would produce high-density, anomalously slow seismic material at the base of the mantle. This hypothesis connects the ULVZs, the superblobs, and the early evolution of Earth's atmosphere into a single narrative chain. The oxygenation of the ocean 3 billion years ago produced iron oxide sediments. Those sediments were eventually subducted. They sank to the core mantle boundary. They accumulated at the edges of the superblobs, and they now sit there as ULVZs, their ancient origin recorded in their extreme seismic properties. A 2025 paper examining the detailed structure of the lowermost mantle around the Pacific, LLSVPs, found evidence for a slab-like high-velocity sheet slipping beneath the northern edge of Jason, cold subducted oceanic lithosphere pushing under the superblob, displacing material horizontally at the core mantle boundary, potentially generating new ULVZs and reshaping the plume generation zones at Jason's edges in real time. The interaction between subducting slabs and the superblob edges is not a historical process. It is happening now. The deep Earth is dynamic on timescales of millions of years, not static, not passive, but actively responding to the ongoing machinery of plate tectonics above it. What the ULVZs do, functionally, in terms of the deep Earth heat engine, is also a matter of active research. Their position at the edges of Tuzo and Jason in the plume generation zones suggests they play a role in the initiation of mantle plumes. The buoyancy of a mantle plume depends on the temperature excess of the plume material relative to the surrounding mantle. A starting material that is already at the hottest, most buoyant point at the base of the mantle, and that may already be partially molten, reducing its effective viscosity, would be an ideal source for a rising plume column. The LLVPs may be the spark plugs of the deep earth heat engine, the sites where the heat transferred from the liquid core into the base of the mantle is most concentrated, where the material is most ready to rise, and where the plumes that will eventually feed Kilauea and Iceland and Réunion first detach from the base of the mantle and begin their millions of years' journey to the surface. If this model is correct, and the evidence increasingly suggests it is, then the chain of causation connecting the deep earth to the surface is core cools, transferring heat to the base of the mantle at LLSVP edges. LLVPs develop at these edges, concentrating heat and possibly partial melt. LLVPs provide the hottest, least viscous starting material for mantle plumes. Plumes detach and rise through the mantle over tens of millions of years. Plumes reach the base of the lithosphere and produce hotspots. And occasionally, when conditions are right, when the plume head is exceptionally large or the lithosphere is unusually thin, a plume produces a large igneous province, flooding the surface with lava volumes that can destabilize the climate and drive mass extinctions. The LLVPs are not merely a seismic curiosity. They are the deepest, hottest, most extreme environments in the solid Earth, and they are the origin points of the most catastrophic volcanic events in Earth history. The next supercontinent, Amarsia, as it has been dubbed by geologists who model the future trajectory of plate tectonics, will form in approximately 200 to 300 million years. As the Americas drift northward and collide with Eurasia across the closing Arctic Ocean. The configuration of Amarsia will be different from Pangaea, rotated approximately 90 degrees relative to it, centered on the Arctic rather than the equatorial Atlantic. The subduction pattern that will assemble Amarsia will reshape the flow of the deep mantle, potentially reorganizing the positions and configurations of Tuzo and Jason as new subducted material piles up at the core mantle boundary in new locations. The plume generation zones will shift. New hotspots will form. Old ones will weaken. Large igneous provinces will erupt in locations that are currently tectonically quiet. The surface of the Earth will be remade, as it has been remade multiple times before, by forces that ultimately trace back to two hot blobs of anomalous material sitting right now at the base of the mantle. The future of Tuzo and Jason, and through them, the future of the Earth's surface, is a question that geodynamic modeling is only beginning to address with the sophistication the problem requires. The assembly of Amarsia, the next supercontinent, predicted to form in approximately 200 to 300 million years as the Americas drift northward and collide with Eurasia across the closing Arctic, will be the most direct test of the relationship between superblob configuration and supercontinent geography that the geological record will ever provide. Unlike the reconstruction of past supercontinents, which requires reading backward from fragmentary evidence, the formation of Amarsia is a forward prediction that current models can calculate with increasing confidence. The critical question is what happens to Tuzo and Jason as Amasia assembles. The most widely discussed model, the orthoversion model proposed by Ross Mitchell and colleagues, predicts that Amasia will form approximately 90 degrees from the location of Pangaea, centered over the Arctic. In this scenario, the closure of the Arctic Ocean brings North America and Eurasia together. The Atlantic eventually closes, and the new supercontinent sits approximately orthogonal to Pangaea's position. The subduction geometry that assembles Amasia will be dramatically different from the subduction geometry that assembled Pangaea, and therefore the flow of cold subducted material to the core mantle boundary will be different, potentially reshaping the positions and configurations of Tuzo and Jason over the timescale of Amasia's assembly. What this means for the plume generation zones at the edges of the superblobs, and therefore for the geography of volcanism on the surface, is that the hotspot map of the Amasia world will be fundamentally different from the hotspot map of today. Hotspots that are currently active, Hawaii, Iceland, Reunion, Yellowstone, may weaken or shift as the plume generation zones at the superblob edges migrate in response to the new subduction geometry. New plume generation zones will develop at the new edges of the reshaped superblobs. New hotspot chains will appear in locations that are currently tectonically quiet. And somewhere, in 200 million years, or 250 million years, or 300 million years, a new large igneous province will erupt from one of these new plume generation zones, flooding a landscape that currently exists only in geodynamic simulations, with lava volumes comparable to the Siberian Traps or the Deccan. The East African Rift will not wait for Amasia. Within 20 to 30 million years, a new ocean basin will be opening between the Somali Plate, carrying the Horn of Africa, and the Nubian Plate carrying the rest of the continent. Africa is in the process of splitting, and the mechanism is Tuzo. The plume beneath Eastern Africa is doing now what the plume beneath the Central Atlantic did 200 million years ago when it began splitting Pangaea, weakening the lithosphere from below, creating the conditions for rifting, eventually opening a new ocean. The geological record suggests that this process has happened before, repeatedly, driven by the same superblob edges. The Red Sea, the narrow body of water separating Africa from the Arabian Peninsula, is a young ocean, approximately 30 million years old, currently in the early stages of the same process that will eventually widen it to the scale of the Atlantic. The Gulf of Aden, to its southeast, is similarly young. Both are products of the Afar plume, a particularly active upwelling from the edge of Tuzo, pushing Africa and Arabia apart. The Afar Triangle in northern Ethiopia, where the East African Rift, the Red Sea Rift, and the Gulf of Aden Rift all meet in a three-way junction, is one of the most extraordinary tectonic landscapes on Earth. A place where you can stand at sea level and watch three tectonic plates simultaneously pulling away from each other, the Rift Valley floors dropping below the elevation of the sea, the ground fractured and steaming with the heat of the mantle rising below. The Afar Triangle is not merely a geological curiosity, it is a real-time demonstration of continental rifting in progress. the same process that opened the Atlantic 200 million years ago, happening now, at the pace of a few centimeters per year, driven by a plume that originates at the edge of Tuzo, 2,900 kilometers below the surface. The connection between the superblobs and the history of life on Earth extends beyond the mass extinction events discussed earlier. The breakup of supercontinents, driven partly by the plumes generated at superblob edges, has been one of the primary mechanisms creating the geographic isolation that drives speciation. When Pangaea began breaking apart approximately 200 million years ago, the fracturing of a single continuous landmass into multiple separating fragments created biological barriers, growing ocean basins that isolated populations and drove them along different evolutionary trajectories. The dinosaurs that colonized the northern continents after the Triassic-Jurassic extinction had a different evolutionary history from those on Gondwana, and ultimately produced different lineages. The mammals that diversified in the Paleogene did so on continents that were geographically separated in ways that promoted rather than suppressed diversification. The extraordinary biodiversity of the modern tropics, the Amazon Basin, the Congo Basin, the Southeast Asian archipelago, reflects in part the history of continental positions that were themselves determined by the plumes generated at superblob edges. In this sense, the superblobs are not just the engineers of catastrophe. They are also, indirectly, the engineers of biological diversity. The rifts they open, the oceans they create, the geographic barriers they establish, all of these contribute to the conditions under which new species form and existing lineages diversify. The most productive moments in the history of life on Earth, the Cambrian explosion, the Triassic recovery after the end Permian, the Cenozoic mammalian radiation, occurred in geographic contexts shaped, at least in part, by the long-term influence of superblob-driven plumes on continental geography. The deep Earth and the history of life are not separate stories. They are the same story, told at different scales and at different depths. There is a temptation in discussing structures of this age and scale to reach for language of permanence and immutability. Tuzo and Jason have been there since before the dinosaurs existed. They may have been there since before any multicellular life existed. They have survived everything. They will outlast everything we know. But this framing misses something important. The Earth is not a static machine with permanent parts. It is a system that has been evolving continuously since its formation, driven by the slow loss of the heat accumulated during accretion and by the decay of radioactive elements embedded in the rock. The heat budget of the Earth is finite. The Earth is cooling, slowly but measurably, over geological time. The vigor of mantle convection is decreasing. The rate of volcanism at hotspots and mid-ocean ridges is decreasing. The rate of plate tectonics itself may be decreasing. In several billion years, when the Earth's interior has cooled sufficiently, mantle convection will slow to the point where it can no longer sustain the plate tectonic system. The plates will cease to move. The recycling of oceanic crust through subduction will stop. The generation of new oceanic crust at mid-ocean ridges will stop. the planet will become tectonically dead, like Mars, like Mercury, like the Moon. A world with a solid surface, no volcanic activity, no magnetic field generated by a convecting core, no mechanism for cycling carbon between the interior and the atmosphere. The conditions that make Earth habitable, including the carbon silicate cycle that regulates atmospheric carbon dioxide and maintains surface temperatures within the range. Liquid water can exist, will cease to function. When that happens, Tuzo and Jason, or whatever remains of them by that point, will cease to generate plumes. The hotspots will go cold. Hawaii will stop building. Iceland will stop erupting. Yellowstone will go quiet. The plume generation zones will become relics of a geologically active past. The East African Rift will either complete or stall. But that is billions of years away. Right now, in 2025, we are in the middle of a geologically active period, with two superblobs energetically generating plumes at their edges, with the East African Rift actively splitting a continent, with Iceland erupting regularly, with Kilauea flowing into the Pacific. The deep Earth machinery is running at full capacity. The two structures at the base of the mantle that we discovered less than 30 years ago are doing what they have been doing for most of Earth's history, heating the base of the mantle, generating plumes, driving hotspots, and occasionally producing the flood basalt catastrophes that periodically reset the biosphere. We are living on the surface of a planet whose interior architecture, the two vast thermochemical structures at its base, the plumes they generate, the plates they drive, the volcanoes they feed, is still largely unknown to us. Seismic tomography has given us the first outlines of Tuzo and Jason, the way a very early map gives the first outline of a newly discovered continent. Enough to know that something large is there, not enough to know its interior geography, its history, or its future behavior. The abominable mystery is not Darwin's, it belongs to geophysics. Two continent-sized structures at the base of the mantle, managing most of the planetary volcanism, possibly 4 billion years old, made of material we cannot directly sample and cannot yet fully characterize. We know they are there. We know roughly what they do. We do not know what they are. That gap between what we can observe through the behavior of seismic waves and what we can actually understand about the composition, origin, and long-term evolution of these structures is one of the most significant gaps in current Earth science. Closing it will require better seismic networks, better computational models, better laboratory experiments at extreme pressure and temperature conditions, and possibly new observational approaches that have not yet been invented. The history of planetary science is a history of discovering that the obvious, accessible surface of a world is not where the interesting things are. The interesting things are inside, in the cores, the mantles, the deep interiors that cannot be directly seen or touched. In the case of Earth, the most interesting things are two enormous hot blobs sitting at the base of the mantle, directly above the liquid iron core, generating the plumes that feed the volcanoes that have shaped this planet's surface and biosphere for hundreds of millions of years. We named them after two of the greatest geologists of the 20th century. We are still, in the 21st century, just beginning to understand what they are.